Okay, welcome to week 5 of the CAD class. A little bit of weird situation this week. If you guys are watching this live, what you're actually watching is a premiere of a pre-recorded video that have done. I had a conflict and I couldn't actually be at my computer to record this live at the time we were scheduled, so I just pre-recorded it. I probably am actually available. I'm just not on the recording. Obviously I will not be able to answer questions live because it's pre-recorded, but I will be checking, as this is premiering, I will be checking the YouTube chat and the RoboChargers chat and everything, and Chief Delphi and everything. I'll be available for questions, on my phone. So if you have questions, go ahead and just put them in the chat, but I won't answer them on the stream, obviously. So, um, RoboCharger students, you guys should still be in a call, and so some of the other mentors can answer your questions as well in the call, and I may, depending on how things go, I may join the call late. So let's go ahead and get started here. So this week we are going to be talking about some gearbox stuff. Our COTS highlight are planetary gearboxes, and then our engineering concept is actually going to be a little bit of a kind of, I don't know, a design exercise, I guess, preparing us for our CAD project in the latter half of the class. So I will get more to that when we get there. We're going to go ahead and start with the COTS highlight this week just to kind of get it, because it doesn't tie in quite as closely as the engineering concept and the CAD segment do. So I'm going to go ahead and do this first, just as a little bit of background, and then we'll move into the second half. So, all right, planetary gearboxes. So first of all, we mentioned the term gearbox a little bit last week when we were talking about gear trains. So let's just talk about what is a gearbox. Basically, a gearbox is just a self-contained gear train in some sort of a housing. It's the kind of the key thing is it's self-contained, which means, it can be its own unit just sitting on a table, basically, right? It's not this like special integrated thing that's, part of the overall structure of the robot or whatever machine it's part of. So typically gearboxes have several different features. They obviously have all of the gears. Typically those gears are on some sort of shaft, and those shafts are supported in bearings. All of those components are part of the gearbox, and the gearbox kind of serves to locate and support and protect all of those components. Like I mentioned, generally speaking, a gearbox is assembled separately as its own standalone unit, and then it's mounted to the robot as a finished unit, as opposed to being, kind of integrated into the structure of the robot. Generally speaking, at least in an FRC context, a gearbox often provides a mounting interface for the prime mover. In the case of FRC, that's an electric motor. If for other things, maybe industrially or whatever, that's not always the case, but usually in FRC, it does provide a motor mounting interface. A lot of gearboxes also have an enclosed housing, meaning there's no gaps or holes or vents or anything. And that's basically just to keep dust and debris out. Typically, the gearboxes are not like completely sealed, so like they're not airtight, but they're kind of just there to keep dust out. That's not quite as common in FRC. Obviously, think about the transmission on your car or whatever. Like all of those are very tightly enclosed to kind of keep environmental factors from affecting the gearbox. But that's why these are typical features, is because they're not. This is not true of every gearbox. It's just kind of in general what you would expect to see. So that's what a gearbox is in general. Now, what we're going to talk about is a specific type of gearbox. So we're talking about a specific type of gearbox called a planetary gearbox. A planetary gearbox operates using what are called epicyclic gear trains. Hopefully I'm pronouncing that correctly. Don't think I've ever said that word out loud in my entire life. Most of the time we just call it a planetary gear set or a planetary gear train, but epicyclic is the kind of technical term for it. Basically, It is a system of spur gears. You can see this image over here on the right side of the screen. It's a system of spur gears that are rotating inside of a ring gear or an internal spur gear. We talked about last time we talked about different types of gears. We talked about ring gears. We talked about spur gears. Planetary gear set is kind of a combination of a couple different types: the internal spur gear and then a normal spur gear or an external spur gear, if you like. And they're kind of in this arrangement here. So there's a few key components. So first of all, the outside, the internal gear is just called the ring gear. That's easy, right? The sun gear is this gear here in the center, and then the planet gears are these gears around the outside. A couple things. There can be different numbers of planets. There's 4 in this screenshot that I grabbed. This is of a planetary gearbox used in FRC. I just grabbed a screenshot of a CAD model just to kind of show you what it looks like. The size of the sun gear and the planets can vary. So these are kind of roughly the same size. But the sun gear can be much larger and the planet's much smaller, or the planets can be much larger and the sun can be much smaller. There can be different numbers of planets, like I mentioned. So there's kind of the different configurations there that are possible. But those are the 3 key components: is the ring gear, the sun gear, and the planets. And as you can imagine, as the sun gear rotates, the planets kind of roll around the outside, and so the planets kind of as the sun gear spins, the planets just kind of migrate around in a circle, and that's why they're called planets, right? Because they kind of orbit the sun, right? It kind of looks like a solar system, right? So that's why it's called that. Okay, so let's talk about a little bit more about a typical planetary gear train. Their planetary gear trains or epicyclic gear trains are actually somewhat complicated in terms of how they can be used. There's a lot of different ways to use them. Epicyclic gear trains can actually be used as a differential, which is a special kind of mechanical device that I don't really even want to get into. But like there's a lot of different ways to use them that you don't ever see inside of FRC. There's really only one arrangement that's used in FRC. So I'm going to describe that here to you, and we're going to talk about it, because that is the only way they're used in FRC, and it is the most common way they are used in general. But there are other arrangements. So if you kind of want to do your own looking into planetary gear sets, if you come across some weird example where they're not using the like which gear is driven by the motor and which one is spinning, and if you come across a different arrangement, just understand that that is still probably a planetary gear set which you're seeing. It's just being used differently. So okay, so the sun gear is driven by a motor, or it's driven by a previous gear stage. Get to that in a second. But the sun gear is what is driven. So you've got some sort of shaft or torque transfer interface that's spinning the sun gear. You can see this little view here. This is the sun gear here in the middle, and then you got the planets outside, and then I made the housing kind of transparent. This is once again a CAD model of a gearbox used in FRC that I just used as a screenshot, but you can kind of just imagine the outside could look like anything, right? But we've got the sun gear here, which is being driven by a motor, and then we've got the 4 planets that are kind of just revolving around the outside as the sun gear spins. The ring gear, most importantly, is fixed. So the ring gear is basically the housing of the gearbox. In FRC, that is always true. Outside of FRC, that's one of the things that can change. Sometimes the ring gear will spin and other things will be locked in place. So there's kind of some weirdness there. But in FRC, the ring gear does not spin. It's stationed in a static location. Typically, like you can see on this screenshot, you can see there's bolt holes. This whole thing gets bolted in place and it doesn't move. So the sun gear spins, the planets kind of revolve around at the outside, and the ring gear does not move at all. Now, the key thing here is that there's this thing, which you can see on this bottom render, called the carrier plate. And it's basically just a plate, and it's got these pins sticking out of the plate. And the pins kind of go into the centers of the planet gears, and the planet gears can just free rotate around those pins. And then basically, as the sun gear spins and the planets kind of migrate around between the sun gear and the ring gear, these pins, they're rotating, they're spinning around the pins, and the pins are basically kind of following them along as they orbit the sun, right? And so basically that causes the carrier plate to spin. And then basically you use the carrier plate as the output of your gearbox. So the sun gear is the input and the carrier plate is the output. And because the planets are they're kind of they're kind of moving slowly as the sun gear rotates, you basically get a gear reduction there. Now I will say I can show you the math behind a planetary gear set, and I will. There's a slide on it here up soon. I don't know if it's the next one or no. So it's a little bit difficult for me. I haven't. I mean, working with planetary gear sets for years, I have not actually found a good intuitive way to explain to people why there's a gear reduction there, like why the planets orbit so slowly. It's not nearly as intuitive as like a normal gear reduction, right? You think about, oh, small gear has to go around 3 times before the big gear turns once, and so there's a reduction in speed there. It's like that's very intuitive using a normal gear set. Planetary gear sets are kind of a little more complicated. They're kind of harder to wrap your head around. And so it's the thing to understand just is that the planets they kind of orbit around the sun as the sun is spinning, and they orbit slowly. They don't orbit fast. They're spinning relatively fast because they're just engaged with the sun. But the fact that they're kind of rolling around the ring gear is causing them a reduction in speed, and that's where you're getting this gear reduction in the planetary gear set. So I don't really have a better, more intuitive explanation for it than that. If you want a little bit more, kind of hands-on experience with this, I mean, you RoboCharger students, you're welcome to look at the planetary gear sets that we have in the shop. We've got a bunch in a drawer. I can pull them out and show it to you, and you can kind of just play with it in your hands. That's a good way to kind of see this work. There's also plenty of little animations on YouTube of these running. A ton of 3D printing channels, 3D print planetary gear sets and use them for different things. So if you guys kind of want to get a more gut feel of what a planetary looks like in action, go ahead and do that. If I had been smart, I would have taken a video and embedded it in this presentation, but I didn't think of it. So that's all the explanation I can really give. You get this gear reduction. The carrier plate turns much slower than the sun gear, and you get a reduction in speed, and you can use that to slow a motor down and gain torque. Okay, so let's talk about why you would use a planetary gear train as opposed to a normal just spur gear reduction. So the key reason is they have higher torque capacity for the same size gears. And the reason, the real reason for that, the main reason for that is because if you look here, however many planets I have, each of the planets is sharing the torque on the sun gear. And so on a normal planetary gear set, you basically have one tooth on the pinion and one tooth on the gear loaded. You basically just have one tooth on each gear touching each other. And so basically all the force has to be carried by that one tooth. And so if you overload the gear and that one tooth breaks, right, the gear fails, right? In a planetary gear set, because you have multiple gear meshes, each of those gear meshes are actually sharing the load. So you can kind of think of it like, this planetary gear set that I'm showing here has 4 planets. So you can kind of think of it as having 4 times the torque capacity that a normal spur gear reduction would have, assuming that the gears are the same pitch, right, the same size, right? Because 4 teeth would have to break in order for the gear stage to fail, kind of. Or the load is shared 4 ways as opposed to being borne by one set of teeth. So you just get this giant multiplier on if I've got 4 planets, I basically just get 4x the torque capacity, roughly speaking, and so I can use that stronger torque capacity to then make my gears smaller, right? So I can use big gears and have really big torque, but if I don't need that much torque, or torque capacity, I mean, you can make the gears a lot smaller, and it basically just, you get a very high torque capacity in a very small package. And so really that plays into space efficiency, right? Planetary gear sets do a lot of reduction and have a lot of strength packaged in a very small space. And so that is a huge advantage, space efficiency. The other thing too that goes along with space efficiency and like using smaller gears, a ring gear. I mentioned this when we talked about ring gears in the other presentation. Ring gears, because of the way that the tooth profile is shaped, ring gears are actually a very strong shape. And so you can actually use weaker materials that are lighter, and the ring gear teeth won't fail. So like we'll talk about it a little bit later, but most ring gears in FRC gearboxes are made out of aluminum, but the planets and the suns are made out of steel, and that's because the ring gear tooth geometry is so strong, you don't need to make it out of steel to have it be strong, and so you can make it aluminum and you save a ton of weight, right? So you get the strength of ring gears in a small package. You also get the strength of ring gears in a lightweight material, which is a super big advantage to save weight. And making your gearbox smaller also saves weight as well, so that's kind of an additional advantage. The other thing is when we look at the diameter of the ring gear, uh, you think about a spur gear that's that same size and like what kind of a reduction you would get from the sun to the ring gear. Like you would get whatever the ratio is between the counts of the teeth. Um, with a planetary gear set, because the reduction is happening in kind of a weird way, you actually end up getting more reduction than you would expect. I have this little equation here. The reduction of a planetary gear stage is the ratio of the ring gear teeth divided by the sun teeth. This is actually the reduction, right? So this is not gear ratio. This is gear reduction, as I defined it in our previous thing. So if you want the gear ratio, it would be you'd take this whole equation over 1. But so like ring teeth divided by sun teeth, and then you add 1, right? You just get this adder. And once again, I don't have an intuitive explanation for why that is the case. That's how the math works out, and it's a little bit hard to kind of wrap your head around, but that is true. So for example, if I have a 60-tooth ring gear and I have a 20-tooth sun gear, that's a 3-to-1 ratio. But the planetary gear stage is actually 4-to-1 because I have this +1 on the end of the equation, right? And so if I did that with spur gears, if I had a 20-tooth pinion and a 60-tooth gear, that would be a 3-to-1 reduction. But if I do it in a planetary gear, I have a 4-to-1 reduction, and also I have the added advantage of the sun gear is kind of packaged inside of the ring gear, and so it's this super compact thing. And then on top of that, I get the extra torque capacity and stuff that we already talked about. So you just get this like kind of compounding factors with planetary gears. And so then the other thing too is because the whole gearbox is kind of axial, right? I'm driving the sun gear and the sun gear's in the middle, and then I have the carrier plate. I mean, in this case, there's this spline in the carrier plate, and that's how I'm getting torque out. I have something that sockets into this spline. But this carrier plate is rotating around the same axis as the sun gear is. So what I can just do is, as long as I have the proper splines and shafts and stuff to interface, I can just take one planetary gear set and stack another one right on the end, have the carrier plate drive the sun gear of the next stage, and I can stack these reductions and create multiple stage gearboxes in this really crazy compact and super easy to manage kind of form factor. And so on top of all the other advantages, the fact that you can just kind of stack these end to end to end to end and just keep going, you can create these crazy high reductions if you want to, just by stacking these stages on the end. That has some very specific advantages when it comes to FRC and FTC, and I will go into those later. Okay, so a quick summary on planetary gearboxes. They're very high performance, they're very small, and because they're small and because they're very efficient in terms of the gear strength, they are also very light. They are extremely ubiquitous inside of FRC and FTC because, in the case of FRC, weight is extremely important and space is important. FTC weight is not quite as big of a concern, but space is definitely a concern in FRC because the robot's really small. The only disadvantages that spur gears have is that they are complex, which means they can be more expensive. So you're not going to see planetary gear sets on, cheap items like, appliances or toys or things like that, you're usually not going to see them there because the performance is not usually worth the cost. You will, however, see tons of planetary gearboxes in like industrial applications. A lot of cars have planetary elements inside of the transmission, and you'll see them in robotics, like in obviously FRC and FTC, but also in other robotic application as well. So planetary gear sets are just, there's a lot of advantages, at the relatively small cost of some complexity. So that's kind of an overview there. So let's talk, now that we've talked about planetaries, let like kind of conceptually, let's talk about some actual specific ones. Obviously, we're talking about ones that are off the shelf, and I'm focusing on ones that are marketed towards FRC and FTC. Obviously, because planetary gearboxes are super ubiquitous, for a lot of applications, you can go buy industrial ones and, hobbyist ones and, whatever. And so I'm not going to cover those. I'm just covering the ones that are targeted at FRC, FTC kind of markets. Okay, so let's start here. Gonna cover some ones off the bat that are kind of less common, and then towards the end, I'm gonna hit some of the ones that are a little bit more important for you guys to know. So there's a few different companies that are gonna make these. I know that I haven't really addressed the whole like supplier thing, and so I'm gonna throw out some names. And I understand like if you guys are new, you guys might not know who these companies are, but I'm just gonna kind of throw them out, explain just briefly who they are, and then move on. In the previous iteration of this CAD class, I had a little bit more on introducing some of the companies that we commonly buy from, but I'm just going to kind of overview these a little bit. I also mentioned there's some kind of regional stuff, like depending if you're on the robochargers, we're going to use certain suppliers, and if you're watching this video and you're from a team in a different part of the country or a different part of the world, you may use stuff from a different supplier. So okay, so BaneBots has a whole line of gearboxes. They have P6, P7, P8, and then they've got a few different like grades of each one. So they've got like light duty, heavy duty. I think there's normal duty for P6 and P7 and heavy duty for each one, and then P8 I think has 3 like normal, heavy duty, extreme duty or something. So they've got like a bunch of different like kind of levels of gearbox. They go all the way down. They go all the way down to like relatively low torque, like rollers in FRC, kind of that torque range, and they go all the way up to like super high torque, almost to the point where you would never even see those levels of torque in FRC. So it's a very, very broad range depending on which one you buy. So these are really not used in FTC. I don't think I've ever seen one of these gearboxes used in FTC. I could be wrong, but they're really, really not common. And they're not really common in FRC either. You will see them, but they're not super common. They have quite a few disadvantages. So they're generally just very heavy. They're not. There's a lot of kind of like inefficient positioning of material and stuff in them, and so they don't make quite as good of use of the weight in the gearbox as they could. They are not. I don't want to say that they're not modular. And this is something that we're going to talk about. I mentioned how stacking stages was a very useful feature in FRC. The gearboxes that we're going to get to a little bit later are actually modular. You can change the gear sets out. You can swap them in these little packages, and you can kind of put the gearbox together the way that you want to get exactly the gear ratio that you want. These gearboxes, in general, you just have to buy them off the shelf with the gear ratio that you want. And once you buy the gearbox, you can't change its gear ratio. You just have to buy a different gearbox and replace it. In general, these can be disassembled, so like you could kind of change the gear ratios if you want to. So that's why I wouldn't say that they're completely not modular, but they really are not modular. They're assembled from the front, which is annoying because you can't take the gearbox apart while the gearbox is mounted to something. But that's not a huge issue because the gearbox is not modular anyways, so you're not taking the gearbox apart to change modules. You're just taking the whole thing off and replacing it. All of these have a keyed shaft, which keyed shafts used to be more common in FRC, and they just really aren't anymore. Hex shaft is pretty much the only thing teams use. So keyed shaft makes these gearboxes super hard to use. The other thing is they don't have a face mount. I forgot to put this on the slide. I mentioned it later, but they only mount with these holes in the side, which in an FRC and FTC use case is far more difficult than face mounting. We'll talk about a little bit more of that to get to some of the other gearboxes. So, all right, next slide. This is the Sport series of gearboxes. These are sold by AndyMark, which is another supplier. They're out of Indiana. AndyMark is a really big FRC supplier. They sell to tons of teams. Tons of teams use their products. Robochargers, we don't really buy from them that often, just because we've got both Vex and Rev here in Texas, and so we can get parts from them super fast. And we kind of just generally prefer their products, anyways. Kind of explain that a little bit later, but so we don't actually buy that much stuff from AndyMark, but lots of other teams do. So they have their Sport line of gearboxes. The Sport gearboxes are actually manufactured by BaneBots. So these gearboxes here on this previous slide, that company actually makes these gearboxes. So they have a lot of similarities, but they're slightly better optimized for FRC and FTC. So this little red block up here is their like Never Rest series of gearboxes, which go with AndyMark's FTC motor that they have, which is called the Never Rest. And so these are used in FRC, FTC. I feel like I don't see them that often, so I don't actually have a good concept of how common they are. Like I said, it's kind of a regional thing. So like here in Texas, you're not going to see them as much because teams are buying more locally, like from Rev or Vex or whatever, rather than getting stuff from Indiana, shipped in, because shipping's more expensive. So they might be a little bit more common depending on where in the country or the world you are, but I don't really see them that often. Then they also have their like bigger Sport line. So it's the 57 Sport, the Sim Sport, and the Falcon Sport. And those are really just they're all the same gearbox. They just have like a slightly different kind of collection of parts depending on which motor you're using. So the actual like gearing part, I believe, is the same across all of them, but and the output shaft and everything is the same. But it depends on what motor you're using. The 57 Sport, by the way, is called a 57 because it's 5 for 500 or 550 series motors, and it's 7 for 700 or like 775 series motors. So it's 550 or 775. That's what it's compatible with, those motors, and there's multiple motors in that family. So the Sport gearbox is somewhat common in FRC. Like you see them around. You definitely see more of them than you see the BaneBots ones, because it's targeted at FRC markets. It's got a hex shaft output, and it's got like easier motor mounting for motors that are being used in FRC. So another advantage of these gearboxes is they have pretty good torque capacity. They're not like top torque, because they're not the same as the biggest BaneBots gearboxes. They're more the small size, but they're like, in terms of their size and their weight, they have pretty good torque capacity. At the time that they came out, they were pretty much the highest torque capacity Planetary gearbox in the FRC specific market outside of BaneBots' offerings, which a lot of teams couldn't take advantage of because just of the weight and the shaft and stuff. So they have a few disadvantages. Once again, they pull a lot of the disadvantages from the BaneBots gearbox line. They're kind of heavy. They're a little bit better optimized than the like kind of normal BaneBots ones, but they're still relatively inefficient on weight. They're once again not modular. They can kind of be disassembled and swapped, but like they're really not modular. You buy the ratio that you want, and then you replace the gearbox if it's not right. They're assembled from the front. Once again, that kind of doesn't matter because they're not modular anyways. So even if you could assemble them from the back, you couldn't do anything with that because you have to replace the whole gearbox to change the gear ratio anyways. Like I said, some kind of asterisks to that stuff, but that's kind of just a general overview. I don't want to get too into the weeds on this. And then it doesn't have a face mount. It only has the side mounts. You can like take these front screws out, which is actually the screws holding the gearbox together. You can actually take those screws out and use those screws to mount the gearbox on the face of it, but that means that once you take those screws out to remove the gearbox, the whole gearbox kind of falls apart. So that's a thing. So these are not, these like don't have like super great like market share in FRC. Like they're not super crazy common, but they're common enough that you'll see them around. Okay, so next slide here. So this guy right here, this is the VersaPlanetary. So this one is made by Vex. This is the original modular gearbox in FRC. Vex is here in Texas. They're in Greenville, so they're relatively close by for us robochargers. This gearbox came out in it came out for the 2013 season. So it's been around for a while. The BaneBots has had gearboxes around longer than that, but they've actually gone through like at least one like product reset where they kind of discontinued all their gearboxes and came out with a new version. So like the BaneBots gearboxes that were out when the VersaPlanetary was launched were slightly different, but still kind of the same concept and a lot of the same disadvantages. So BaneBots gearboxes were pretty common. Reasonably common, I would say, before the VersaPlanetary came out. And then when the VersaPlanetary came out, I mean, it just took over because the VersaPlanetary was so much of a better product that, I mean, everybody switched overnight. 2013 was my junior year as a student, so I had done 2 years of FRC before the VersaPlanetary came out, and then my junior and senior year we used the VersaPlanetary, and it's just like night and day. Was so much easier to use than the products that existed before. So VersaPlanetary is extremely common in FRC. Like basically up until the last couple of years, you would basically see a VersaPlanetary on every single robot in FRC with only a few exceptions. Like crazy common. They have, so it is fully modular. I'll talk about that in a second. They're fully modular, and it was the first fully modular gearbox in FRC. And then a few years later, they came out with a version of the gearbox that had a plastic ring gear that was and a plastic housing and stuff that was a lot lighter and saved a lot of weight for FTC. And so they have a light version in FTC, and they're not super common in FRC. I see, or FTC, I mean. I see a few of them, but I don't see like a ton. I actually see more of the light versions just used on FRC to save weight and for light duty applications. So that's a thing. So it has a lot of advantages. It's got a hex shaft output, which is great. It makes much better use of its weight and volume and everything. As much aluminum as there can be. You know, a lot of weight save, kind of thin walls and stuff that just makes good use of the weight. So it's very lightweight and it's very efficient in terms of the weight. It has, out of all the gearboxes we're going to talk about, it has the most versatile input options as far as I know, which means you can basically take any motor that's used in FRC and plug it into this gearbox. So that part's super good. The first version was not assemblable from the back because that was kind of not a feature that people cared about. Like the first version was like modular, which is a big deal. And then like a couple years later, it wasn't very long, they came out with like a V2 that was then assembled from the back. So the current VersaPlanetaries that everybody's using these days, they're all assembled from the back, which means that if you want to change the gear ratio of the gearbox, you don't have to take the front part of the gearbox off of your mechanism, right? If you've got the gearbox driving, you know, a roller or an intake or something, and you don't have to disconnect it. You just take the back part of the gearbox off, which just has the motor and the gear stages, and you replace the gear stages to change the gear ratio, and then you put it back together. Now, earlier I didn't really talk about why that's an advantage, so I want to talk about that real quick. I want to kind of keep moving through these slides, but I want to address this. So with this image here, the motor would be on the back, kind of, it's not in this picture, but like the motor would mount back here, right? This area here, you can kind of see these little creases on my screen. This block here is just kind of an input block that just kind of it just does the adaptation from the motor shaft to the gearbox. And then this little guy here in the middle is actually the housing that includes the ring gear, and this is actually the gear stage. And then this block here that has the shaft in it, right? This is just the output block, which has like bearings and stuff just to support the shaft. And so if you want to change the gear ratio, you can add or remove gear stages. You can do no gear stages. You can do one gear stage. You can do two. You can do three, and change the gear ratio. And there's different gear stages that have different reductions. So they've got a 3-to-1, 4-to-1, 5-to-1, 7-to-1, 9-to-1. They've got a few different ones, right? They've got different ratios, and they all have the same form factor, but you can drop in these little kind of different ring. The ring gears are all the same, and you drop in these like different gear sets on the inside. I'll talk about that in a second. So modular is super great for doing mechanisms where you don't exactly know what the optimal gear ratio is to balance like torque and speed. Having a modular gearboxes are super nice. The other thing that's super nice about modular gearboxes is that you can just buy a whole bunch of them before the season starts. You don't have to like buy specific ones like, okay, this is a gearbox that's good for an arm. This one's good for an elevator. This one's good for a fast intake. This one's good for a slow intake. This one's good for, an indexing roller. This one's right. You don't have to like split out all these applications. You just buy a bunch of gearbox parts, a bunch of modules, a bunch of gear sets, right? You put them in a drawer, you have them in your shop, and then when the season starts, you assemble the gearboxes you want, and it's great. And then the fact that they're assemblable from the back means if you screw up and you don't pick the right gear ratio and it doesn't work very well, you just take the gearbox from the back, you put different gear sets on, you change the gear ratio, you put it back together, and you're up and running again. So it's super big advantage. So couple problems here. So they have kind of, so because the ring gear and the gears inside of it are separate, it's kind of, it is kind of difficult to assemble because when you take the thing apart, there's so many little pieces inside the gearbox and there's nothing really holding them together. They all just kind of fall apart. In addition, there's kind of some interlocking features and the order that the thing assembles and like which screws you have to use where. And because of the versatile motor mounting thing, like the motor mounting area can be confusing. And it is like a major chore to assemble these gearboxes. I really don't like doing it. It is pretty difficult. In addition, it is super difficult to explain to somebody. It is a very difficult gearbox to teach someone to put together. And so it is a very labor intensive, difficult thing to create. And when you're in a high pressure, build season where you don't have a lot of time and like you've got a bunch of people that you're trying to like, get coordinated, make sure everybody has something to do, like sitting down and spending a whole bunch of time assembling gearboxes or explaining to someone how to assemble gearboxes is like, it's a big ask. So it's really not a good experience from a assembly standpoint. And if you're in the pit and you're trying to swap a gear ratio or replace a gear set quickly and you drop one of the little parts, like you're out of luck. It's just a bad experience. So a lot of advantages, great product, but in terms of the assembly and all that stuff, it really can be a pain. Also, it's because it's pretty small and because it's a lot of aluminum and it's very light, it doesn't really have that high of torque capacity, especially in more modern FRC where we're using these like really high power, high torque motors. It's compared to some of the gearboxes we're going to talk about and compared to the Bainbots and the 57 Sport and all that, it really doesn't have that great of torque capacity. It's much better for like more higher speed applications. So like rollers and intakes and indexers. It's like borderline good enough for like a high power elevator. It gets used for that. It's pretty good for that. You can use it on a climber, but you got to be careful about like kind of what the gear ratio is. And then for like really heavy stuff like arms and things like that, like where there's a lot of torque, it's just you're not going to be able to use it for that very effectively. And then they do break, right? So like they, if you over torque them, they break, which is true of any gearbox, but because it's not that high of torque capacity, it's it breaks relatively easily. The other thing is when you're using it with more of the motors that we're using these days, like higher power motors, like the Neo, kind of the Falcon, the Sim, these motors that have these bigger style motors are actually compatible with this gearbox. This gearbox is more meant for a smaller class of motors, but people don't use those motors as often as they did a few years ago. And so with like the Neo and the Falcon and the some of the other motors that we're using, you have to modify the motor shaft or replace the motor shaft to be able to use it with this gearbox, which is what didn't used to be as much of a problem, but it's more of a problem now because we're using these bigger motors more often than we used to be using the smaller motors, right? So that's kind of a problem. The other thing that's annoying about it is this shaft that sticks out the front is like it's only a certain length, and it ends up being, for a lot of applications you use it for, it ends up not being a good length. We'll kind of talk about that a little bit here in a second. So great gearbox. We've got a bunch of them in the shop. And we've kind of moved on to some other gearboxes so we don't use these as much anymore, but a lot of teams still use them. We keep them around for spare parts in case we have alliance partners or whatever that need parts as well. So still super common in FRC. Okay, so UltraPlanetary. So all right, so this gearbox and the next gearbox, these are manufactured by Rev Robotics. I work for Rev Robotics, so I'm slightly biased. So forgive me for that, but so the UltraPlanetary is an FTC specific gearbox. It is pretty much able to handle, like torque wise, it's pretty much able to handle anything in FTC that you need to throw at it. And then it is also useful in FRC for low load applications. Now I know I was like kind of just talking about a few different types of motors on the last slide. We have a segment in the CAD class where we're going to talk about motors, and it was supposed to be this week, but I decided to do this slide instead because it made more sense to pair the motors up with a different topic. And so in a few weeks, the motor discussion is coming up, but it's not this week. So I understand if I'm throwing out some motor names, you might not know what those are. So I apologize for that. I'll try to keep my motor mentions to a minimum because it doesn't necessarily do anybody any good. So these are compatible with the Neo 550, which is the smaller of the two motors from Rev Robotics, the brushless motors, I mean. So it's compatible with Rev's, the HD Hex motor, which is Rev's FTC motor. On robochargers, we only use the HD Hex motor. That's the only motor that we've used. There are other motors that are FTC legal, but if the robocharger students listening to this, if you guys remember the motors that we used last year, those are the HD Hex motors. So you guys also probably remember putting together the UltraPlanetary gearboxes. We used quite a few of them on our FTC robots last year. And then that same gearbox is compatible with the Neo 550, which is the little tiny brushless motor that we use in FRC. Robocharger students, we had our swerve module had Neo 550s on them. We had UltraPlanetary stages on the swerve module for steering the wheels and everything. So you guys have definitely, if you guys have, gone through a season of FRC with robochargers, you guys have definitely seen these. This is a newer product. I don't know how old it is, maybe 4 years. Don't quote me on that one. This one was designed before I started working at Rev. But basically it has fully self-contained gear stages. So one of the things that this gearbox tried to do, especially since it was for like an FTC market where teams are in classrooms and stuff, like you didn't want a bunch of little small parts falling all over everywhere. So like the VersaPlanetary has issues with. So the gear stages actually have, I should have put a screenshot or a picture in here of the actual individual gear stage, but you can see the little clips on the sides here, but they have these little covers. And so the ring gear and all the little gears and stuff in the carrier plate and everything inside is all held inside this little cartridge. And so that cartridge is a single unit and you can't take the cartridge apart. And so what the cartridge does is you can, pick it up in the air, turn it upside down, shake it all over the place, and you're not going to lose any of the planet gears or any of the little pieces inside the planetary gear set. And the other thing too is like this gearbox looks the same size as all the other gearbox, but it is a very small gearbox. And so the fully self-contained gear stages makes assembly of this gearbox super, super easy. So that's a big kind of improvement over gearboxes that have existed on the market before. So A couple other advantages. It's extremely lightweight. A good chunk of this gearbox is plastic, kind of taking advantage of the ring gear being the strong part. Some of the gears inside are steel, right? And so like it's making very good use of its weight. So its torque capacity for its weight is pretty good. It's very, very small, like I said. Now it is meant for an FTC application, so its torque capacity and everything are not, that high. But for low load applications, it's pretty efficient. The other big improvement of this gearbox over all the other gearboxes that we've talked about is it has a socket output. So you can kind of see it in this image here. There's this like hexagonal socket in the front of the gearbox. So instead of having a shaft sticking out of the front of the gearbox like all these other ones do, this has a socket, and you put your own shaft into the socket, and the hex drives whatever shaft you install in the gearbox. And so what that allows you to do is, choose whatever length of shaft that you want. In addition, this gearbox also has this kind of screw pattern. This whole thing spins. And so like if you want to 3D print something to bolt onto this bolt pattern and spin with the gearbox, you can. Or, Rev has line of, pulleys and gears and different and sprockets and different things that bolt onto this bolt pattern. So you don't have to use a shaft at all if you don't want to. You can just use the bolt pattern. So let's talk about some disadvantages. So one thing I didn't mention, this gearbox does assemble from the front. That's kind of unavoidable just to keep the gearbox small and space efficient, but it does mean if you want to swap the gear ratio, you have to take the gearbox off. So that's a disadvantage of this gearbox. It does have low torque capacity, like I mentioned, so it's only suitable for low load stuff in FRC, but it's able to handle pretty much anything you can handle or anything you need to handle in FTC. One of the big annoyance things about this gearbox is that it has the different gear slices. There's different gear cartridges available that have different ratios, just like the VersaPlanetary. However, they're not exact integer numbers. So like the VersaPlanetary has like a 3-to-1 stage and a 4-to-1 stage and a 5-to-1 stage, et cetera, et cetera. The UltraPlanetary, they're nominally 3, 4, 5 are the 3 stages that are available, but they're not actually quite exactly the right ratio. They're an approximation, and that's because of some of the kind of the details of the gear train inside that's causing that to be the case. It doesn't have it's not a functional problem. Like it doesn't hurt performance at all. Actually, the part of the reason is that it actually improves performance, but I don't want to get into that. But the non-integer gear ratios does mean that it's still a little difficult to do like head math to try to figure out exactly what your gear ratio is. You're like, oh, you can't really just like take it's a 3 stage times a 4 stage, it's a 12-to-1. Well, it's not quite 12-to-1. So like doing some head math around and quick math around gear ratios gets kind of more difficult, which is kind of just an annoyance. It doesn't really cause any problems. It's just kind of an annoyance. There's limited motor compatibility. It's only compatible with the HD hex motor, which is used in FTC, and motors that have that same shaft. And then it's only compatible with the Neo 550, which is that little brushless motor for FRC. Now, the good news is the gearbox is well optimized for those two applications, so that's generally okay. But if you wanted to use it with a different motor and gearbox, you can't, or a different motor on the gearbox, you can't. There's a couple other motors in FRC that would really benefit from being compatible with the UltraPlanetary, but it is not compatible with them. Like I mentioned, it's assembled from the front. It does face mount, which is nice. The other weird thing about it is it's metric hardware. It's metric because it's used for FTC and everything, and FTC is metric primarily. But for FRC, that's a little bit weird because most FRC stuff is inch hardware, inch dimensions, and everything. Something else I should mention: the VersaPlanetary has side mounts, and it also has face mounts. The UltraPlanetary only has face mounts, so that's a bit of a limitation as well. And that's just once again because it's a super compact design. There's no space for side mounts. Okay. So last gearbox. All right, this one is also another Rev gearbox. This one is my baby. I actually designed this one myself. This is one of the big projects I worked on at Rev. One of the first big projects I worked on at Rev. So this was one that I designed. So once again, I'm slightly biased, so bear with me.
This one is relatively new. This was new for the 2022 season, so the season that we just completed. It is for FRC. It's pretty large if you wanted to use it in FTC. You can, but it's quite a bit larger than the UltraPlanetary. This is made specifically for Neo class motors. So I mentioned on the VersaPlanetary that mounting Neo class motors, like the bigger, more powerful motors that we're using more commonly these days in FRC, mounting those motors to the VersaPlanetary was difficult, and also the torque capacity of the VersaPlanetary is not as favorable for those bigger motors. And so the Max Planetary is an FRC gearbox targeted at these higher power, higher torque motors. And so it is built so that you don't have to modify the motor shafts at all. You can plug the motors in right out of the box into this gearbox. The other big thing is it follows along with the same kind of I guess design philosophy as the UltraPlanetary. So you can see kind of the same kind of clips, same kind of clip design as you saw on the UltraPlanetary, these like shields, and basically the gear stages are these cartridges that are completely self-contained. So you can take them out of the gearbox and like I said, shake them around, wave them around, whatever, and the parts won't fall out, right? They're all fully contained. There's a lot of advantages to this gearbox, and it kind of just continues to build on some of the UltraPlanetary, the nice UltraPlanetary features, and kind of continue to improve upon them for this larger gearbox. So this has extremely high torque capacity. It's got a lot more torque capacity than the VersaPlanetary. It has more torque capacity than the Sport line of gearboxes, and it has more torque capacity than most of BaneBot's gearboxes, although their big gearboxes have a higher torque capacity than the Max Planetary. However, they do so at the expense of a lot of weight. So the Max Planetary is a little on the heavy side, but it makes good use. It makes good use of the weight that it has and provides a very high torque rating. It has a socket hex output similar to the UltraPlanetary, so you can put whatever length of shaft in you want. It's half-inch hex, so it's super common shaft in FRC. The other thing that it has that's not really fully integrated into the UltraPlanetary is that there's a screw, like if you before you assemble the gearbox, there's a screw that can hold the shaft in this socket output. That's a nice feature so that you don't have to like have some other retention method to keep the shaft from like sliding out the end of the socket. The UltraPlanetary has a set screw for that feature, but set screws are kind of iffy. They don't necessarily hold very tight. They're more okay in FTC, but in FRC, set screws are kind of a big no-no. Like I said, okay in FTC and FRC, you typically want a different shaft retention method. So for the Max Planetary, it has a screw that holds the shaft in, and that screw can't come loose. It has the same cartridge system as the UltraPlanetary, but the gear ratios are actually integer gear ratios. So when it says 5:1, it's actually 5:1. So it makes like head math and doing quick calculations for gear ratios easier. That's more just a convenience thing. It doesn't really, it doesn't really have any functional advantage. The other thing is it is assembled from the back. It has face mounts. It has face mounts in a couple different orientations, and it also has side mounts. And so it's got a lot of advantages. Like I said, it's new. So to be fair, it is, in my opinion, it's better than a lot of the gearboxes that have existed before. But it has also had the advantage of building on kind of this history of planetary gearboxes that existed in FRC. And a lot of great products that have come before it. So you can see there's a lot of features here that we talked about on some of the other slides that are important. Okay, so then, like I said, disadvantages. It's kind of on the heavy side. It's a kind of large, but in general, it has a smaller cross section than the motors that are mounting to it, so that's not usually an issue. And then the other disadvantage is that it has lower reduction stages. So like the ones that are in this picture, the 3, the 4, and the 5, those are the only reductions that are currently available for it. and that has partially to do with the motor compatibility and everything. And so like if you compare that to like a VersaPlanetary, you know, you for the Max Planetary, there are some gear ratios where you need more stages. Like you could do a 2-stage gear ratio on a VersaPlanetary, but it would take 3 stages with the Max Planetary or something. There's not very many of those situations. Like if you work through the gear ratio like chart, but there's a few of them, so where you end up having to have more stages than you would really want to have. But that is all at the expense of, or that was all done because of the torque capacity of the gearbox. So. All right, this presentation went super long. Obviously, I cannot answer any questions live in this video, but if you have questions, go ahead and post them in the YouTube chat. You can post them in the Chief Delphi thread, or you can post them in our Slack channel if you're a RoboCharger student. Also, if the RoboChargers are on a voice call, you guys can ask some of the other mentors in the voice call if you guys have questions. So if everything goes according to plan, I will answer your questions relatively live here. Like I said, I'm pre-recording this video, but I will probably be on my phone while this video is premiering. So, okay. Sorry that went so long. A lot of important information there. When you guys are designing robots, you will actually spend quite a bit of time designing with planetary gearboxes. So it's very important that you guys understand kind of what's available. And like I said, you know, the RoboChargers don't use all those gearboxes. We primarily last year on our robot we only had UltraPlanetaries and Max Planetaries. Like the 2 Rev gearboxes were the ones that we used. So those are the ones that you'll probably need to get used to using the most in upcoming seasons. All right, let's move on to our next topic here. I'm going to try to go through this. This is not super complicated, but I'm going to try to go through it relatively quickly just so we don't go crazy over on time here. I don't think this is going to be a full 30-minute thing, so I was okay running over on the last one. Okay, so we are doing a project. We are moving into the part of the CAD class where for our pre-recorded CAD on shape tutorial sessions, we're not actually going to be doing like me demonstrating little, you know, how to use this tool, how to use this tool, how to do a sketch, how to do an assembly. We're not going to be doing that. We're actually going to be doing a design project, and I'm going to be teaching you how to use some more advanced features and things as we go through the design process of designing something that is like kind of actually useful, right? We're going to be designing little chunks of mechanisms or little modules or something that like you could see on an FRC robot. Excuse me. So this for this week and next week for the CAD sessions, we're going to be doing a 2-stage gearbox design. And so for our engineering concept this week, we're going to talk about what is the process of designing a 2-stage gearbox, mostly mathematically. I'll address that here in a second. But yeah, we're going to kind of do the design work for it, like the upfront math stuff for it. I'll show you how to do that stuff. In general, we're not going to be doing engineering concepts related to our projects every week. This is kind of a special situation this week because we need to kind of spend some time on the math before we go into the CAD. So, you know, next week we'll have a different engineering concept that's unrelated to this project, but we're going to be working on the CAD aspect of this for 2 weeks. Yeah, that's kind of the what's coming up here soon. So, okay, so let's talk about why you would design a custom gearbox. Because we literally just went through a whole bunch of super great off-the-shelf planetary gearboxes. They're modular. You can change the gear ratio. Okay, why would you use anything except one of those planetary gearboxes? And that's a very good question. And the answer typically is that you don't, you would, right? You don't design a custom gearbox. You typically use an off-the-shelf gearbox, right? If you have an application where you can use an off-the-shelf planetary gearbox, you probably should. There are a few reasons why you would build a custom gearbox, though, or design a custom gearbox. So one of the reasons would be weight. In certain very, very specific situations, you might be able to get your custom gearbox to be lighter than a planetary. Now, I mentioned in the planetary segment that the planetaries are very light, they're very weight efficient. You're not going to be building a custom planetary gearbox because that would require manufacturing resources beyond what most FRC teams have available to them, including robochargers. So you're not going to be building custom planetary gearboxes. You're going to be building spur gearboxes, which are typically not as weight efficient. However, in certain very specific situations, you might be able to take advantage of some structure that's already on the robot, or you won't have the full housing like the planetary gearbox has, so you're kind of shedding some weight there. Weight might be a reason to design a custom gearbox. The more typical reason is probably space, right? Planetary gearboxes are long and skinny, and that doesn't always play very well on an FRC robot. Sometimes you'd rather have like very short and flat, I guess. I'm not sure how to describe it, but like the opposite of long and skinny, right? So sometimes planetary gearboxes don't physically fit in your robot very well, and so designing a custom gearbox that has a very different shape saves you a lot of space in your design. Strength is one thing. We talked about a lot of planetary gearboxes. The majority of them are not particularly high torque. The Max Planetary is higher torque than anything that's kind of really been on the market or commonly used before, but it's also relatively new, and there's applications where maybe you wouldn't want to use a Max Planetary, and so a spur gearbox with a 20 DP spur gears, which are relatively large teeth, would be pretty strong. The other reason to do it, this is also another common reason, is that you need a very, very specific gear ratio. This is typically on your drivetrain. Elevators is also another common example of this as well, where you really want to optimize a mechanism for like acceleration and covering a distance in a certain amount of time. You really need to optimize it based on its torque versus speed and all this stuff. And so that kind of complicated optimization process, you really need a very specific gear ratio to accomplish that. And for like a planetary gearbox, all you can do is swap out a cartridge. Or you can swap from a 3-to-1 to a 4-to-1, and that doesn't give you a ton of granularity. And so a very specific gear ratio would require a custom spur gearbox usually. Okay, so let's talk about a quick overview. What does the design process look like? Okay, first of all, you determine your specifications, like what kind of gear ratio do you need, or like what kind of output speed do you want, what kind of torque do you want, whatever is driving the gearbox. I'm really not going to go into that process too much, especially not this week. Determining the specifications for a gearbox is kind of a complicated, kind of multidisciplinary FRC, FTC kind of task. A lot of times, if you guys are first year CAD students, really I'm probably just going to do that and kind of walk you through the reasons for why the specifications are what they are, but I'll do the heavy lifting in terms of math. And then once you guys have like a year of design under your belt, we'll kind of walk you through the process of determining these specifications a little bit more so you can do it on your own. So I wouldn't worry too much about determining the specifications in your first year of design. That's not something that like first year design students are going to do. That being said, we did talk a few weeks ago about like the concept of like calculating torque and moments and like your lever arm and how much force is applied and how much torque you would need to lift an arm of a certain weight. We kind of talked about that. That's kind of the type of stuff that's going to go into determining the specifications. How much torque do you need to lift your robot and whatever. Later in the CAD class, we are going to go through the common motors used in FRC and what their specifications are and how their performance is calculated and everything. So you'll have a little bit more information about how the gearbox specifications are generated from doing that module as well, but that's much later. That's several weeks from now. Okay, so then once you determine the specifications, like what torque you need, what speed you need, whatever is driving the gearbox, you're going to just calculate the gear ratio based on what motor you're using. When you calculate the gear ratio too, you'll need to figure out how many stages you need. If it's a pretty high reduction gearbox, you'll need maybe 2 stages, maybe 3 stages. But if it's a low gear ratio, maybe you can just do it in 1 stage. And by stages, I mean I'm talking about compound gear, a compound gear train, which we talked about last week. I'll show you some screenshots if you don't remember what that is. Okay, so then once you calculate the gear ratio for the whole gearbox, you need to calculate the gear ratio for each stage individually. And then once you kind of have an idea of what each stage's gear ratio is, you need to choose gears. And then basically the process of 3 and 4 is kind of an iteration. So like once you choose the gears, you're like, oh, I can't get the gears to produce this exact gear ratio, so I'm going to go back and revise the gear ratio for this stage and then adjust for it on the next stage. And then you kind of just go back and forth, like just picking gears and calculating gear ratios and then repicking gears and recalculating gear ratios until you get close to what you need. Then basically you're going to lay it out in CAD to make sure that the gears all fit and everything is laid out nicely. We talk about what that means more in our actual CAD videos later. But if there's some problem in your layout in CAD, you have to go back and repick gears, recalculate gear ratios. And then once you're all good to go there, you do the rest of the CAD model. You do the full detailed CAD model, which is once again is another thing we're going to cover in our CAD video later. Okay. Let's talk about, I'm just going to throw some specifications out there. I'm not really going to talk too much about it. These are somewhat random. I don't exactly know what these specifications would be used for. I just came up with some specifications that, kind of made an interesting gearbox. So we're going to be using the Neo 550. It's a small brushless motor. It's the one that steered our swerve modules and ran a bunch of rollers on our robot last year. So current RoboCharger students, you guys have seen these and played with these. New RoboCharger students, you guys will definitely come into contact with them. We're going to do a plate and standoff design. Talk more about in the CAD videos what that means. We're going to do a 2-stage compound gear train. So this kind of screenshot over here, this is not the exact gear train that we're going to do. This is just an example of what a 2-stage compound gear train looks like. Compound gears are these gears that are sharing the shaft. We mentioned that last week, I believe. And then 2 stages, just that this is a stage and this is a stage. And so it gives you a higher reduction in a smaller package. So specific specifications, we need our, the output freeload speed of the gearbox needs to be 750 RPM. I'll go through the math for how we figure out gear ratio from that here in a second. We're going to use 32 DP gears for the first stage, or 0.8 module gears for the first stage, and the second stage will be 20 DP gears. That's somewhat arbitrary. I really just kind of wanted a little bit of variety in the gears for this project, just to kind of get you guys used to working with different hardware. In reality, RoboChargers really don't use 32 DP gears that much. Other teams do, like lots of teams do. 32 DP is pretty common. The RoboChargers don't really use them. There's some examples of using them, but we didn't use any last year, for example. But we have in previous robots. So we're not going to use them a lot. We mostly use 20 DP gears just because they're convenient. But yeah. And so the reason you would use the 32 DP gears in the first stage is because there's going to be lower torque in that first stage, and you'll use 20 DP gears in the second stage because it's higher torque. Specifically for this application, I don't really think it matters, but I just did that to just kind of mix it up and kind of add some variety in the mix. One quick note, 0.8 module gears are not exactly the same thing as 32 DP, but they are so close that they are functionally equivalent. You can use 0.8 module gears and 32 DP gears pretty much interchangeably, as long as you're careful. Especially when you're talking about a single gear stage, just one pinion meshing to one gear, you can definitely do it. Okay, so let's figure out our overall gear ratio. So we want 750 RPM on the output shaft of the gear. The other thing I think I mentioned, I did mention it. I want a 1/2-inch hex shaft output. Which that'll be pretty easy to achieve, but that's a thing we're gonna have. So that 1/2-inch hex output needs to be doing 750 RPM when the motor is not under load. So the Neo 550's free load speed is 11,000 RPM. So we figure out U is the variable I'm using for gear ratio here. We figure out what the overall gear ratio of the gearbox needs to be by taking the output RPM that we want and dividing it by the input RPM. Now this is gear ratio, not good gear reduction. If you don't remember my definitions for those terms, you can see the presentation from our gear segment last week. So you can see here on the screen, there's this equation. We're taking 750 RPM, dividing it by 11,000 RPM. The units cancel out, whatever, we get this 0.0682, right? Or that's equivalent to 1 to 14.67. So it's basically slowing the motor down by a factor of like 14.67. It's obviously a weird number, right? It's not an integer gear ratio. Okay, so let's talk about the next step in our process. Now we know the overall gear ratio of the gearbox. We need to figure out what is the gear ratio of each stage, because we got like one stage that's here, and then we've got one stage that's here. Once again, these are not the exact gears that we're going to be using. This is just a representative screenshot of what our gear train will kind of roughly look like. Generally speaking, you usually want each stage in a multi-stage spur gearbox to have about the same ratio. I don't want to get too into the weeds on why that's the case, but basically keeping all of the gears the same size helps you save space on the overall gear packaging. It also helps decrease the total rotating inertia of the entire system. So like you have less, it takes less motor to spin up the gears, right? Because the gears have some inertia, and so like the effort to spin up and spin down the gears like is a small factor. It's like a couple percentage points in a gearbox like this. That's much more important on like a drivetrain, and even then it's still a small fraction. But like it's just a good thing to do if you have the choice. So generally speaking, if you have all the same gear pitch, right? So like we are using 32 dp on the first stage and 20 dp on the second, so all of our gears are not the same pitch. But if they were all 20 dp gears, generally speaking, you would want the earlier stages to have a slightly less reduction or slightly smaller gears than the later reductions. If you have a smaller gear pitch on the first stage, like we do in this example, you can do more reduction on the first stage than you can on the second because the gears are smaller. So if you kind of look at this example, you see how big this this gear down here is, right? If I wanted to put this whole thing inside of a housing, this gear here being so small it's kind of just creating wasted space. And so I could take this gear and make it bigger and then add more gear ratio on the first stage and take some gear ratio away on the second stage by making the second gear smaller. And I would end up with an overall smaller gearbox housing that has the same overall ratio. So we're probably going to do that on our gearbox, and we'll talk about that in the next slide. So to figure out kind of if we want every stage to be exactly the same ratio, we can calculate that by raising our overall gear ratio, which we calculated on the last slide, to 1 over the power of the number of stages. Okay, and if this looks a little confusing, basically remember 1 over a number of the power as an exponent, I should say, is the same thing as taking the root of that number. So let's make this a little bit easier. We have a 2-stage gearbox. S is 2 in our case, right? And so 1 over S, raising something to a power of 1/2, right? 1 over 2, 1/2. That's the same thing as taking the square root, right? The second root of the number, the square root. If we had 3 stages and 1 over S was 1 over 3, right? Raising something to the power of 1 over 3 is the same thing as taking the cube root, right? The third root. And so this equation maybe looks a little intimidating, but like, it's actually pretty simple. You're just taking the root of the number of stages of your gearbox. So we take our overall gear ratio, 0.0682. We basically take the square root of it. That gives us 0.2611, which you'll notice is a larger number, because it's less of a ratio. And that's equivalent to 1 to 3.830. That basically meaning each stage is slowing the shaft down by a factor of 3.83. So that if we want the stages to be roughly the same reduction, this is the ratio we're going to go for. Okay, so typically you start when you're picking out physical gears, like you're actually picking products to buy and put in your gearbox. You basically you typically start with the pinion, which is the small gear that goes on the motor. The reason that you do that is because typically you typically have less options for that product, and so you're the most limited by what you pick there, and you typically have more options for the other gears in the gear train. That's like somewhat unique to FRC. If you were building a gearbox for not FRC and you were doing custom stuff and all the gears were custom, you could do whatever you wanted. But we're talking about specifically building a gearbox for FRC. So we need it to we already said we needed it to be 32 dp. That's somewhat arbitrary, but for this project, that's what we're doing. Basically, what you would do is you would look at the motor that you're using, in our case, the Neo 550, and you would basically just check through the typical FRC suppliers. Right? You look at Rev, you look at Vex, you look at AnyMark, you look at West Coast, you look at any of the other suppliers, and you basically just look at what gear options they have. For the sake of time, I'm not going to take you guys onto the websites and look through that process. There will be, not in the CAD videos this week, but in the CAD videos next week, I'll be going through some suppliers' websites and kind of showing you guys around. So I'm going to just take my word for it. I already did the legwork. I picked out this pinion, and you guys will kind of see more about that process like a little bit later next week. So we're going to use one from Rev Robotics. Rev makes the motor, so it makes sense that we have the pinion, right? It's a 12 tooth pinion. It's 32 dp. It's actually 0.8 mod, but it'll be compatible with 32 dp gears just fine. Get the part number here. Not that's relevant, but it's 12 teeth is the important number. Okay, so now that we know approximately the reduction that we want our first stage to have, and now we know what our pinion is. So we can actually start kind of solving some equations and kind of finalizing some more stuff on our gearbox. So before I go on, I want to do a quick note, as quick as I can, about math in FRC and in engineering in general. So I will say math was not my favorite subject when I was in school. In fact, I kind of hated it. But as I've gotten, as I get more and more engineering experience and I work in more and more projects, I find myself enjoying engineering math quite a bit. And the one thing that I will say, I'm about to walk through some equations, and last week we had some equations, and this week we have some equations, and I've kind of just made these equations. These are not like super standard stuff that's like from a textbook that you have to memorize. That's not what this is. I mean, all of this gear ratio stuff is really simple, right? It's just this gear's number of teeth divided by this gear's number of teeth, right? It's very, very simple algebra. And I can understand that like looking at this in equations is probably, I don't know, it might not be fun. It might not be very, I don't know, it's just maybe not be very fun. So the one thing that I just wanted to understand is like, I don't really care if you memorize these equations or you even use these equations, right? Engineering does not work like school, right? In school, you have to like show your work and write out all the equations and solve the equations the way that you're supposed to. You're supposed to follow the process, all that stuff. Engineering does not work that way. Now, there is certainly a place for engineering documentation where like if you're doing a bunch of complicated equations, that is, guidance for your rocket that's going to orbit, and you don't write it down anywhere and you do it all head math or the calculator on your phone or something, right? Obviously that's going to cause problems. So like there's certainly, don't let me discount the value of engineering documentation and making sure that your math is checkable by another person. However, in the context of FRC and in the context of just kind of a more simple engineering math that's not, guiding a rocket to space, you don't need to show your work, right? You need to solve the problem. The goal is that you solve the problem. Right? It doesn't matter how you solve the problem as long as you get it right. And so, and I think, I was in a similar situation to the situation you guys are probably in now, where math is just not fun for a lot of people, and it's just not enjoyable, and it's kind of ruined by the fact that like you'll be given a math problem and you'll feel like you know how to solve it, and you have your way that you want to solve it, and you're forced to use a different way of solving it. But like, let me tell you right now, I am going to show you a way of solving it that looks great on these presentations. But if you have a different way of solving these problems, you can solve it however you want to, right? You do not have to do it my way. You can do it your way. You can do it however you want. And most of the time you don't have to show your work, right? You need to calculate the gear ratio of some gearbox or whatever. You can figure that problem out how you want to. You can use my equations, you can figure out your own, you can use gear ratio, you can use reduction, you can do whatever you want to do. All you have to do is just figure out the simple math for how many teeth does this gear need to have. You need to solve the problem. And that's what I like about engineering math, is because it really isn't about the process. It's actually about the end result, right? Which is a kind of a super rewarding thing to work with, I guess. That's not, you don't necessarily run into every day. It's really just about like, can you get the right answer? It doesn't matter how you got there. And so I just wanted to, before I dive into some of these equations, I'm going to kind of just gloss over them. If you guys want to look at the slides and kind of pick out the equations in a little more detail, you can. But I just want you to know, I just built these equations out because I need to have some way of showing the math on a slide deck. But it's, not super mission critical to what we're doing here. So anyways, the gear ratio of the stage is the gear ratio of the input gear, the number of teeth on the input gear divided by number of teeth on the output gear. Plug in our numbers. We know the stage gear ratio, or kind of what we want, and we know the input gear, but we don't actually know the output gear. So you use algebra, you rearrange it if you want to, and you basically get this equation here, and this spits out basically the desired number of teeth on the output gear, which is for the first stage would be like this gear here, right? And obviously it's not a round number, right? So we got to pick a gear, we got to pick a physical gear that has like close to this number of teeth. So it wants basically 46 teeth. And then basically we go on our suppliers, we look on the websites, we look at options we've got. We don't have a 46 tooth 32 DP gear available. Rev has 42 and 56 tooth 0.8 module gears. Those are nice because they're actually 0.8 module. They're once again, they're compatible with 32 DP, but they're technically 0.8 module, and so they will mesh very well with our motor pinion. However, they are 5mm hex, and for this gearbox, 5mm, because they're FTC gears. So for this gearbox, 5mm hex isn't really going to work that well. So Vex has a 40 tooth and a 60 tooth available in 3/8 hex. Robochargers don't really use 3/8 hex for shaft a lot. I didn't have any on the robot last year. Personally, I hate 3/8 hex shaft. I know a lot of teams use it, so there might be people like throwing things at their monitors right now hearing me say that, but like personally, I'm just not a fan. I don't like having to deal with 1/2-inch hex and 3/8 hex stuff and like remembering which is which and keeping both in stock on hand. It's just, I find it to be annoying. The 3/8 hex is used to save some weight and space, and I just find that the advantages are not worth it. However, for this gearbox, because we're trying to kind of mix things up and keep things a little interesting here, we're going to go ahead and use it. So we're actually going to use the 60 tooth gear from Vex. That's 3/8 hex. And the reason we're going to do that is the thing that I mentioned on the last slide, where because we're using a smaller pitch gear on this, or not 2 slides ago, because we're using a smaller gear pitch on this first stage, we can afford to go a much larger number of teeth on this gear and get a much larger gear ratio, because it'll actually end up saving us space overall. Okay, so now we have to recalculate. Now that we chose a gear, and the actual gear ratio that we picked is going to be quite a bit different from the gear ratio that we kind of assumed we were starting with, using that like square root thing. So we are going to just plug in this equation, right? It's just number of teeth on the input gear divided by number of teeth on the output gear. It's 12 teeth on the input gear, 60 teeth on the output gear. That's a gear ratio of 0.2 or 1 to 5, right? So that's our stage 1 reduction. That's kind of locked in place. We've figured that out. Okay, so now that we know that our first stage reduction, we kind of need to figure out, okay, now that we know the first stage reduction, what does the reduction of the second stage need to be in order to produce, the overall gear ratio that we want? So the equation of the overall gear ratio is basically the reduction of stage 1, or the ratio of stage 1 times the ratio of stage 2. We plug the numbers in. We don't actually know the ratio of stage 2, so we kind of do our algebra rearranging thing to rearrange this equation, and we end up getting this guy down here, which is the overall ratio that we want divided by the ratio of the first stage, which we just calculated up here. We divide those out, we get 0.3409, which is the desired ratio for the second stage, which is equivalent to 1 to 2.933, if that's easier to understand. Okay, so typically when you're picking pinions, general rule of thumb, you just want to go as small as possible, right? Because when we're talking about gear ratios, if you make your pinion bigger and you have a gear ratio that you want, you end up having to make your spur gear bigger as well, your driven gear bigger as well. And so you generally just want the smallest pinion possible. There are some reasons not to do that, but I'm not going to go into that now. It doesn't matter. In our case, we're going to pick the smallest 3/8 hex bore gear we can find. It's going to be 20 dp because we said in our specifications that we wanted 20 dp on the second stage. So it's going to be 20 dp. We go through all of our suppliers, Rev, Vex, Andymark, West Coast, etc. Vex has the best selection of 3/8 hex gears. We're going to use their smallest one, which is 14 teeth. They have an aluminum one and a steel one. We're going to use steel. Probably don't need steel because it's a 2-stage reduction off a Neo 550. There's not actually that much torque here, but we're going to just use it because just to add some variety to the mix. So 14 tooth steel gear. So we know we calculated this 0.3409 like gear ratio that we wanted back 2 slides ago for the second stage. We then picked out a pinion. So now we have all the necessary information that we want to do to calculate the number of teeth on the output gear. So this same equation again, we plug in the numbers that we know. We have one unknown, but it's not by itself on the equal sign. So we do algebra, we rearrange stuff, get it by itself on one side of the equation. We end up with 14 teeth divided by our intended gear ratio, which gives us a desired final gear tooth count of 41.07. So we go on our suppliers and we look for which gears are close. We look for, what's the closest gear below this number and what's the closest gear above this number. Rev has 40 tooth and 50 tooth available in 1/2-inch hex and steel. Vex has 40 and 42. Vex generally has every 2 teeth available, but they only have aluminum. So I wanted steel. Like I said, just kind of mix it up. So our first stage gear is aluminum, so I want the second stage to be steel. So we're actually going to go ahead and use the 40 tooth one from Rev. And so that's going to be our last gear. So now we've picked all of our gears. So basically what we can do is we can just recalculate the gear reduction. So the stage 2 gear reduction, we just picked out the gears. It's 14 for the pinion and 40 for the driven gear. Calculate that out. It's 0.35 is the gear ratio, which is the same as 1 to 2.857. 2.857. Yeah, I said that correctly. So then now that we know the gear ratio for stage 2, we can take that number and the gear ratio that we calculated for stage 1, plug them into this equation, multiply them together to get the overall ratio of the gearbox, which is 0.07. Remember, we were shooting for 0.0682, and we ended up hitting 0.07. So it's pretty close. And that comes out to be 1 to 14.29. By the way, this decimal number here that's the gear ratio, and like I made a big point of calculating gear ratio every time. In reality, I do not use this number. I use this number. This 14.29 is a significantly more useful number to me and a more intuitive number. So if this number makes more sense to you, that means that for every 14.29 rotations of the motor, the output rotates once. That's what this means, right? This is the gear reduction, effectively. Okay, quick summary here. First stage is a 12-tooth Neo 550 pinion. Second, the driven gear is the 62 3/8 hex aluminum gear. These are all 32 dp or 0.8 module. Second stage is a 14-tooth 3/8 inch hex steel gear. The reason this is 3/8 hex is because this second stage pinion and the driven gear from the first stage have to mount to the same shaft. You can, make like adaptations to a shaft. So like one part of the shaft is 1/2-inch hex and one part is 3/8 hex or whatever. Right? You can do that. However, it's significantly easier if you just keep the shaft the same. So both of these gears are on the same shaft, and so they have the same bore, the 3/8 hex. And then the output, we wanted it to be 1/2-inch hex, so we used the 40-tooth 1/2-inch hex gear from Rev. So the next steps are to verify the gear clearance in CAD. Using a layout sketch. Go watch the CAD videos. We've got the CAD videos up. I talk about that more in the video, explain what this means, and kind of show you in the actual CAD, like kind of what it looks like. So that's the thing. So once we verify this, if we find any issues, we would have to come back and redo our gear selection. Now, obviously, I did the legwork ahead of time to make sure our gear selections were correct, so that I didn't lead us down a wrong path. So obviously, I'm telling you now, it's good, it's fine. You'll see it in the CAD video, everything clears. However, if you didn't know that ahead of time, you would have to check it in CAD and then potentially come back here and select different gears. And then once you've verified that it's good, you just model the gearbox, which is also covered in the CAD videos between this week and next. Okay. Once again, sorry I ran over. Lot to cover this week. Like I said, I will try to be available come Monday night on the YouTube chat, Chief Delphi, the RoboChargers channel, etc., to answer questions. So obviously this video is not actually live, so I can't answer your questions now. But if you have any questions, please post them in those channels, the methods that I just mentioned, and we'll try to get your questions answered. Quick note, I mentioned this last week. I wanted to mention it again just to give you guys a heads up. Because we are moving into the project portion of the CAD class, basically, you should expect to spend time outside of these CAD class sessions working on these CAD models, following on with the videos and doing these projects. Expect to spend, maybe 2-3 hours on CAD per week working on these projects. I'm going to try to keep them as short as I can, but I mean, at the end of the day, these are relatively complicated design projects, so they're going to be, reasonably time consuming. The videos are also a little bit longer because I'm taking the time to explain what I'm doing rather than just showing you how to physically model something. So expect to block out a little more time. Try to stick with it. This is the part of the CAD class where we start really getting into the meat and potatoes and start actually designing some stuff that's like actually useful on a robot. So thanks for watching. Have fun doing the CAD. Let me know if you have any questions about that as well. And I will see you guys next week.